Hey guys, Joe Pye here at Advanced Innovations. Welcome back to the shop. If you hung in to the very end of the last video I posted, you will know that the next miniature machine that I'm going to build is the shaper. And I've got it laid out on the table behind me. Got all the castings laid out, pulled out of the box, got the prints pulled out. And I'm going to point some stuff out that you may or may not have ever picked up on. It may not mean much to you, but once you notice that it's there, then maybe it will. So let's take a look at the prints. Let's take a closer look at the parts and throw some chips. This is an exploded view of the shaper model. Very well done. And believe it or not, the piece that I'm looking forward to building the most, let me see if I can find it, is this little guy right here. And that's about actual size. That is really small. Looks like a comma. There's going to be some math involved in making that one. Everything else is pretty straightforward. One of the things that jumps off the page when I look at this is how thoughtful they did the bill of materials on the side here. Everything is categorized based on material size, and that makes it a lot easier for the guy reading the print and doing the parts to just leave the machine set up for 1/8" diameter cold roll or 3/16 cold roll, whatever. Chances are if the stock is round, it's all be done in the same machine, right? So good job on that. That is PLV or PLY. Nice job on that one. PM Research model, of course. And I'll tell you my philosophy for doing an assembly like this. A lot of times what you're looking for in the end is for this to work, a functional assembly. That being said, look at all the areas where you need things to interface and slide and articulate and fit. These are the pieces that I will be doing in sequence before I get to the main body of this machine. When all of these pieces are done, these slides and rails and rams, when you're machining your body, you can use that as a functional gauge to make sure that it does articulate the way it's intended. Just a little philosophy. So I'm going to make all the little mating pieces first. These guys are definitely going to be done first because there's an awful lot of T-slots in that. I'm going to set the CNC up on that, and I'm going to give you a little heads up on exactly how a CNC handles that and how easy it really is to do that. Without breaking the tool, we'll see. I only have one tool. Anyway, there you go. Close-up look at the whole assembly view. 62 different pieces in this model and a couple multiples of each, but for the most part, you can see here in the quantity section, it is just 60-something one-off pieces. Quantities drive up when you get to the hardware. Hardware is exceptionally small. Okay, let's take a look at the parts. Take a look at the parts. It's back where they belong. Bag of miscellaneous stock. Everything you need to fabricate all the parts. We got some gear stock. And here are the castings. The castings are very clean. Very clean. Cone pulleys. Doors for the side. Now I can predict right now that drilling these hinge pinholes on the side of this casting to accommodate this door, I'm sure that's going to be fun to get the drill down past the upright and down through these two little bosses. But I'm sure we're going to figure that out as we go along. Nice casting. You can see how big it is. It's about hand size when it's done. It will be a functional machine like all the others. Cool. Let's grab some of these parts, get over to the mill, make some chips. This is the apron casting, and this gets machined 100%. Before I start working on this, I'm going to get the backside, which I've already done, filed out and sanded down to a reliable flat surface. Okay, that being said, a quick look at the print. I'm not going to dwell on anything because it's really not my business to start giving away dimensions. But here are the two pieces. I took 10 minutes and I modeled them up. The green one is the casting and the gray one is the actual part. Now, by aligning the bottom surfaces, I can just take this one and slide it inside the other one. You see me in the background. And by positioning it wherever I want it, I can just say, well, let's just leave it right there. And you can see that the part to be made is entirely inside the casting, which is good. And now I can just measure from plane to plane when it comes time to start milling material off of this. I can put it wherever I want so long as the green is a perimeter around the casting. We're good. I could have done this on the bench with a calculator and sat there for 30 minutes trying to figure out exactly where to make the first cut. But it's a little easier to do this if you have Pro or Fusion or SolidWorks. Learn how to use it. It saves a lot of time when it comes to a part like this. And you can see there's not a whole lot of material on some of those surfaces. But at least I have a starting point. All right, let's get out to the mill, square this thing up, and get it ready for the CNC to put the T-slots in it. Immediately after the center drill operation, I need to drill these holes as deep as I can without popping through the back side. Now the trick that I use to do that is, instead of finding out where the tip of the drill is in relation to the part, I find out where it is in relation to the parallel. Hit the parallel, set your stops, zero your table, and now drop your table a little bit. Now when you come back to that stop with the tool on location and you pull down on the quill until you hit that stop, you'll know that that drill is clear of the parallel, therefore did not break through the back side of that part. It's a great technique. After all the milling and drilling is complete, it's time to do the T-slots. Now let's take a look at how I compose these T-slots, if you can get a look at that. My center slot is always a little bit deeper than the slot on the side. You can see that the 075 channel on the top is deeper. That's because the bottom of this slot basically does nothing. It serves no purpose other than to just stop the bolt if the bolt goes through. So I make the center slot deeper to relieve some of the load on that small cutter. There are 9 of these slots in this part, soon to be, and 3 in the next part in line. That being said, I chose not to do this manually because I didn't feel like cranking my table 10 feet to 2 12 slots. So I wrote a program for the CNC. Let's take a walk over to the CNC, watch this in, I don't know if it's going to be real time or not, but this is relatively quick. It took about maybe 7 minutes to do these 3 slots. and they are not deburred yet. So anybody with good eyes is going to say, hey, I see some burrs in there. Yes, you do. And as far as the kit is concerned, hey guys, PM Research, got to ding you on this one. These scalloped holes here, there is no thickness call out on this top web like there is on the bottom web. It's only dimensioned in one place, and had this dimension been applied up here, you wouldn't have half a hole like that. So unless you have an extended reach 125 cutter to do those counterbores, you might be in a little bit of trouble. So anybody going to do this, make the top surface here 188 as well, and that's 188 Imperial. All right, let's pop this back in the CNC machine. Watch this in real time. I'll also put a compressed version in there if you don't feel like hanging in the whole time, or I'll just give you a real time count on the clock. Let's go watch this machine do that. When you create a program for a feature that's very common across many parts or many different locations, you write a small program, a small loop subroutine called a subroutine, and you just have to tell the machine where to go and do it. So if it takes, I don't know, 25 lines of code to do a cut like that with 2 tools, you don't have to write that 12 different times. You write it one time, you put it in a little can, and then when you go to a different location, you just open that can and the machine cuts it again. And it's as simple as entering one line of code to do that. So I'm going to put these up in the machine. It does change height and it does change distance across the centers of these parts. So where the machine calls 0 is going to have to change in between. All right, let's take a look at how long it takes to actually do a group of 3. I think you'll be surprised. I was very conservative with the programming on this particular part. This is an 075 2-flute carbide end mill, and I am going down as the cutter clears the part. I'm going down about 1/3 of a millimeter, 15,000ths of an inch, and I'm going back and forth. Realistically, this is 9 times I'm taking that pass right there. The benefit to the CNC is the high pressure, high volume coolant gets the chips out of the cutter flutes and reduces the chance of it loading up, heating up, and breaking tremendously. I could never get this series of this volume of coolant on the manual. Everything here is done incrementally, so as the part clears or as the cutter clears, like I said, it's going down 15,000ths on each end and back through it. The cutter is on size to the final dimension, so taking it nice and slow like that alleviates or reduces the amount of flex and therefore keeps it pretty close to the final dimension. This is the T-slot cutter. This is one shot, and this is 10,000ths above, 1/4 of a millimeter above the depth of the slot that's already in there. It relieves a lot of the load off the tool, and since the shank on this tool is only 1.5 millimeters, 0.60, I wanted to relieve as much pressure as I could. Real time, about 10 minutes. It's about 3.5 minutes per slot. It would take me a whole lot longer than that on the mill, so I think I made the right call. Let's do the rest of the parts. Call this one done.